let's start the class. So we were talking about electric potential energy. So you have to imagine that the electric field, okay, is like the gravitational field. So in that case, you see the electric field is uniform because the field lines here are equally spaced. So if you take a positive charge here, you have to do work against the electric field. So you are doing positive work. How do I know that I'm doing positive work? Because you are trying to increase the kinetic energy. So from physics 1, if you are trying to accelerate a system, an object, that means you are doing positive work and you are increasing the electric potential energy. The electric field is doing the opposite. So the electric field, you can think of that as a restoring force. Okay, it's a force that wants to bring the system back to a lower level of energy, lower potential energy. Okay, so it's a restoring force, wants to bring back. So the electric field is doing negative work because it's trying to slow it down. Okay, so the electric field, the electric force is conservative. That means it doesn't matter if I go from here straight up, or if I take that path here, or if I take this path here, the change in potential energy will be the same. Now, if you have, so you can think of that as negative being the ground, and positive is high altitude. So high voltage, and that will be your ground. If it's a negative charge, it's going to be the opposite. Okay, and then we define a new physical quantity, very important, obviously, because it's going to be the voltage, which is the electric potential. Okay, or the potential difference between 2 points. Okay, so in that case, you see the electric field is uniform. So I have an echo. I don't like echo. So the voltage between point A and point B, so this is high voltage, this is low voltage. So the voltage, by definition, is going to be the electric potential per unit charge, meaning for 1 coulomb. So it means if you have 1 coulomb here and you push it against the electric field, the work that you are doing, it's called the voltage. Okay? So in that case, okay, the voltage, we're going to have an easy definition. It's going to be the voltage here, okay, it's going to be E and then delta Y. Okay, so the voltage, so that point here, upstream is always higher voltage than lower stream. Okay, up the electric field, higher voltage, down lower voltage, because the voltage is the electric potential energy per unit charge. So this is right if the electric field is uniform. Okay, you can show that here. You see the work done is just the charge, the force, so QE times the distance. That's the definition of work, right? From physics 1, work is force times distance. So that will be the change in potential energy, force times distance, per unit charge. You're just going to have E times the displacement, okay? And the displacement you just take straight up because the path does not matter. Okay, so you see, you can have that the electric field is going to be equals to, and I should put a delta Y. Oh, I did. Okay, so it's going to be the voltage divided by delta Y. And you have a new unit for the electric field. So far we have seen that the electric field, okay, you can think of the electric field as the force per unit charge. So for test number 1, if you're asked to find the electric field at a given point, you just place 1 coulomb of charge at that point and you're going to find the electric force. Okay, so for example, if you have a positive charge here, it's going to be pushed away. okay, because 1 coulomb of charge is positive. So when you are looking for the electric field for the coming test, imagine that will be the force for 1 coulomb, and 1 coulomb is positive. Okay, so far that was the unit for the electric field. Now we have a different unit which are the same. They are the same, okay? But you have a different way to look at it. You see that the unit for the electric field is the voltage, okay? Because a volt, sorry, and I don't know how to spell. So the voltage, the unit is the volt. So it's going to be volt per unit meter. Okay, so volt per meter. So now we can think of the electric field as a rate. It's a slope. Okay, so you can think of the electric field as a slope, the rate at which the voltage is changing. Okay, so you can think of the the voltage will be the altitude, and then the electric field will be the slope. Now, if you develop volt, then you're going to find the same thing as this. So you have different way to understand the electric field. So now we're going to focus on that. Okay, so just reviewing what we did last time. So again, if now you have the positive charge here and you let go, it's going to accelerate down. So all the potential energy is going to turn into kinetic energy. The electric field is doing positive work because it will make it go faster. Now, if you hold the charge in your hand and you say, okay, not so fast, right? You try to slow it down. So in that case, you are doing negative work because you are slowing it down. So the goal of the electric field is to lower the potential energy. So it's like the electric field, you can store energy in the electric field. Okay, it's a way to store energy in the configuration charge plus the electric field, and then you can get that energy back. So for example, when you are burning fuel, if you are burning carbs or ketone, right? There is it's not chemical potential energy, it's really electric potential energy because of the configuration of the molecules. And when you are burning the fuel to get ATP, okay, you are releasing this electric potential energy. And there is an electron transfer. Right? Electron will lose potential energy, and that goes to ATP. Okay, so they want you to think this is chemistry. This is not chemistry, it's physics. It's not chemical potential energy, it's electric potential energy because of the distribution of charges in the molecules. So anyway, so again, this is from your book, so you have to look at your book, and I don't know where I stopped. Okay, so the voltage, if the field is uniform, if the field is uniform, then the voltage delta V equals E delta S. Okay, so S is just the displacement from here to there. Okay, so that voltage will be larger. So VB is larger than VA. Okay, the negative sign here just means that the electric field wants to lower the potential energy. So that means if you want to increase the voltage, work has to be done against the electric field because again, the electric field wants to lower the potential energy. Okay, is that clear? If the field is not uniform, then you have to use an integral, which is like a sum. This is work. Work done on the 1 coulomb of charge. So let's take an example that few people realize that, but you see when you see this is that you are lucky I made it today. Yesterday I had to cancel my classes because my battery died. because it did like the iguana, okay? Drop dead. Had no battery. I had to call AAA, cancel my classes. You are lucky. One day, just takes one day. So anyway, so you have a battery. This is the positive terminal. This is the negative. So you can think of the negative as the ground. Okay, so we're going to say this is the ground. I like to think of that as the ground. So inside here, you have some chemical reaction, and then it's going to take every single 1 coulomb of charge and give it 12 joule. That's the meaning of voltage. Voltage is joule per coulomb. Okay, the voltage, the units is joule per coulomb. So each coulomb of charge here, because of chemical reaction, is given 12 joule. And then you connect that to a load. So that will be your headlight or your starter. And this energy is going to be dumped into the load. So each coulomb of charge come back with no energy, and then it get a boost again. So imagine 1 coulomb of charge here is carrying 12 joule of charge, 12 joule of energy to supply the load, right? And it depends how many coulombs of charge, that will be the current. But that's the meaning of voltage. Okay? So this is a make-believe. It works to understand, but actually it's electrons. It's the electrons flowing. It's the electrons who are given the energy and then flow through the circuit, give the energy to the load and come back. But just because we love Benjamin Franklin, we're going to pretend it's positive charges. And it's easy to understand if you think of that as 1 coulomb of charge being produced by the battery. Each one of them has an energy of 12 joule delivered to the load, and then they come back with nothing, and then they get a boost again. It's like a pump. Okay? So, but in reality, it's really the electron. So this is the electron. The charge for an electron is E. Remember, it's 1.6 times 10 to the negative 90 joules. Let's forget about the negative sign. Of course, it's going to be negative. It's the fundamental charge. You cannot have a smaller charge than that, because that's the charge of an electron. So each electron will be given an energy from the minus. So they leave the minus, yes, all those little electrons, they leave the minus, and they're going to give that energy to the load. Each electron will have a potential energy of 12 times the charge. Does it make sense? Okay, because what is delta U? The potential energy is the voltage times the charge, because the voltage is the energy per unit charge. Are you with me on that? So if I want the energy in joules, so all I have to do per electron, so the energy that each electron is carrying will be 12 times 1.6 times 10 to the negative 19 joules. But this is annoying because you have a scientific notation and 10 to negative 19. Instead, we're going to say, and this is used in chemistry and nuclear physics, the electric potential energy will be just 12 volt. Okay, so this is 12 volt times E. So E is the charge of an electron. And what is the unit that we get? Huh? What is that unit? EV. 12 EV. So we can define a new unit of energy called EV. Okay? So in chemistry, for example, chemical reaction will involve 1 to 2 EV. If you are doing nuclear physics or radiotherapy, for example, God forbid for cancer, we are talking about mega EV. And if you are doing a particle accelerator, we are in the giga or trillion EV. Okay, so EV is a unit of energy. So each electron delivered by the battery has an energy of 12 eV. Each coulomb of charge has an energy of 12 joules. Are you with me? Yeah? Isn't that interesting? So here we have a 6-volt battery. So this long-term battery for camping, they use that. So that means 6 volt, 6 joule per coulomb from the positive terminal relative to the negative terminal. So some chemical reaction is giving 12 joule of energy per coulomb. And those charges, if you close the circuit, it's gonna deliver that energy to the load. If you increase the number of charges, that will be called the current. What is the current? Will be the number of coulombs per second. So to have more energy, you can increase the voltage, you can increase the current. 9 volt means each electron will have 9 eV, or each coulomb will have 9 joule of charge. Okay, it's voltage here. But a voltage is a property of 2 points. So when you say 6 volt, that means 6 volt relative to the negative terminal. So property of 2 points. You need to have 2 points always. Okay, so here that comes from your book. They have a radiotherapy where they use electron for skin cancer. So very superficial. The EV involved will be between 4 and 20 mega EV. Okay, so if you have a 6 megavolt power supply, okay, it will give each electron 6 MeV. Okay, that's the term that the vocabulary that they will use. You have proton therapy that works better than X-ray and is less damaging when they are doing. The issue with radiotherapy is that for cancer, for a tumor, is that X-ray will destroy not only the tumor but everything in between, right, on the way. So it's very, very damaging, and it destroys the thyroid. For example, if someone has breast cancer, it will destroy it. So there is a less damaging therapy, which is called the proton therapy. Okay, proton therapy, which is up to 250 MeV, but of course, because it's expensive, so insurance don't want to pay for it, so they will only pay for it if X-ray has failed. Okay, it's an issue. But anyway, proton therapy is less damaging because you hit the tumor, but not what is in between. Okay. I'm not going to take a tangent because if I get me started on that, that's another story. So anyway, the electric field does not have to be uniform. You see here you have a strong electric field, and then the electric field is weaker. You can see that with the density of lines. So from A to B, first it's going to be very, very hard to go against it, and then it gets easier. Okay, so the voltage will be the work that you have to do to take 1 coulomb of charge and go from A to B. And for the computation, you want to go straight, because it doesn't matter if you go this way or that way, because the electric force, again, is conservative. Okay, so it's a work. Okay, so it's a work that you have to be doing. See, work is force times displacement. If the electric field is uniform, again, uniform, okay, so it's like doing work mgh, okay, the gravitational field is uniform, just mgh, okay, so the work that you have to do, okay, so delta V, which is the voltage between A and B, so VA minus VB is just going to be E times that distance here. I don't know how to say AB, okay? Just that distance E, delta V. If E is uniform. So that's just the work. It's just work. if the electric field is not uniform, so then you have to divide this displacement in small segments, okay? And then you have to add the work done over every single little segment. So the work done will be the sum of all this little work. So E times that displacement plus E times this displacement times E times this displacement, okay? And that's just going to be an integral. A sum is just an integral. Okay, so you have to do the integral. Now, if I do a graph, here, and I do a E, and that will be the displacement. So let's say E is strong, and then it's going from A to B, and it's going to decrease. From A to B, it's going to decrease. So the work done will just be the integral here. Okay, but it's going to be E times delta S plus E times delta S. So if you take calculus class, remember you divide that when you do a code. If you do coding, for example, and if you want to find the integral using numerical method, because it's too complicated and you got that graph doing an experiment, you have to divide that in small rectangle, right? It's Riemann something. I forgot my calculus class. Riemann sum. Okay? So that will be the integral. That will be the area below that. Okay? So when you are doing work, remember from physics 1, if you are doing work and the force here, and you have the displacement there, then something like this, going from A to B. So the energy transfer, that will be work, it's just the integral. Okay? So it's a review from physics 1 as well. Again, it's not path dependent. Okay? So a battery, for example, if you have 1000 volt, again, what does it mean? It means that each electron delivered by the battery, okay, has an energy of 1000 eV relative to the other electrode, terminal, positive terminal. Or you can say, if it's easier to say, current goes from plus to minus, even though it doesn't, but let's say it does. Each coulomb of charge will have an energy of 1000 joule relative to the negative terminal, which is like the ground. Okay, so that's how we define the unit EV. Okay, example, you have an alpha particle, and alpha particle is two proton. A proton has a charge E, okay, and the voltage is 10 volt. So what's going to be the work done on the alpha particle? See, very good. That's it, right? 2 EV. Okay, because it's the voltage times the charge. That will be the electric potential energy. The charge is 2E times 10, so we say 20 EV because it's easier. Is that clear? So chemical reaction, very low EV, 1 to 2 EV. And then in nuclear physics, that will go to 1000 and mega EV. Ouch. Okay, so how many charges? Okay, let's try to do this one. It comes from one of the free book. You know, the free book I gave you the link in Canvas. I took that from here. Okay, try to do that. So wattage. So what is wattage? That will be 60 watts means 60 joule per second. and you have a given amount of Q, so in Coulomb. Okay, so you don't know how many charges do you need, but the charge goes through 12 volt. So the battery will give, so let's find Q first, the amount of coulombs. The battery, okay, gives, so you have chemical energy to electric potential energy. The battery is giving 12 joule per 1 coulomb. And what is the time? So that, no, I did a mistake. Can you see my mistake? Find the mistake. What are? It's joules per second. Yeah, thank you. Joule per second. 60 joules per second. So watts is power, is the metabolism, how fast energy is being delivered or consumed. So and the time is uh, 1 hour. So in 1 hour, okay, so you can do it in 1 hour, the energy delivered to the load, so load means it's consuming energy, will be 60 times 3600 joules. Do you agree? Okay. So what is joules per second? Okay, it's a rate. How fast energy is being consumed. Okay, so do it. So did you find 216,000 joules? So that will be the total amount of energy delivered to the load in 1 hour. And you know that this energy will be delivered by little coulomb, 1 coulomb. So each coulomb of charge delivers 12 joule. So let's find how many charges do you need to get that amount of energy. Okay, so it's a proportion, right? 1 coulomb is 12 joule. How many coulomb is 216,000? Do it. Don't stare. Staring doesn't help. Montessori says you have to do it. Maria Montessori. So that's going to be very good. 18,000 coulombs. So 80,000, 1 coulomb. But in reality, it's really electrons flowing. So they want to know how many. Oh, by the way, I think there is one question like this. I forgot. I don't know if it's in the makeup or not. But how many electrons? So 1 electron is 1.6 times 10 to the negative 19 coulombs. So if I want to know how many electrons you have to divide, right? Right? So the number of electrons will be 18,000 divided by, open the parentheses. So I've seen that mistake often. Make sure you frame the denominator, because if you don't do that, it will divide by 1.6 and then multiply. 23, exactly, electrons. Okay? But you can you can pretend that if you have a 12-volt battery, this is plus and this is minus. You can imagine that each coulomb of charge leaving the plus has an energy of 12 joule, and that's going to be delivered to the load, and then it comes back with no energy in the hand, and it gets a boost again. As you increase the number of charges per second, you're going to increase the energy, you're going to increase the watt. So we're going to see next that the current is coulombs per second, but that's the next unit. So if you want to find the current, you will say the charge is 18,000 divided by the time is 3600, and you get 5 amps. Okay, so the voltage is 12 volts and the current is 5 amps. So every second, you have 5 little coulombs. Okay, every second you have 1, 2, 3, 4, 5. So if you do 12 plus 12 plus 12 plus 12 plus 12, it's going to be 60. Every second, you have 5 coulomb. Each coulomb has an energy of 12. 12 times 5 is 60 watts. Okay, so 60 joules per second. So we're going to see next that the power is the voltage times the current. Okay, so you can, if you have a battery, for example, you might be surprised that this is 9 volt, this is 6 volt, but this one 6 volt, but this one can deal with a load that are more demanding. This is because it's going to produce more current even though the voltage is smaller. So smaller voltage but more current. Difference between a AAA or a C battery or D battery, it's all 1.5 volt, but the AAA battery doesn't provide the same current. Are you with me? Okay. Okay, so about the electric battery, so we have seen that the first class, right? So that was developed by Volta, and he understood that you need layers. So the first battery here, you had layers, and each cell is made of one copper, for example, some juicy thing, and zinc. Or 2 kinds of metals. You need 2 kinds of metals with some juice in between. So, and then you keep adding up. So, for example, typical, you have a potato battery in series. So you need copper, and here it will be zinc. So the copper give away the electrons. So that will be the positive terminal. And the zinc, it's where electrons are absorbed, right? So that will be the negative. So positive, negative. So that's how you make a battery. And the juice come from the potato. And in chemistry, you usually do that with sulfuric acid, for example, right? Carbon will give away the electron. This one will take the electron. So this one is positive. This one is negative. So that was the discoveries from Alexander Volta, who is Count Volta, because he was knighted by Napoleon. He was Italian, but he liked the French. So he was knighted. But you already know the story because I already told you that. But here, since some of you are in chemistry, what's happening? So the zinc is giving away the electron. So 2 electrons, so it's going to be plus 2 electrons. And I cannot remember if it's oxidation and reduction. So someone told me it's oxidation. I can't remember between oxidation and reduction. Oxidation, you give away electrons. And reduction, you take electrons. So on the other electrode here, you have some, because there is a story with pH. So if you have acidic pH, you have a lot of H plus. Is that right? Okay, so you have a lot of H plus inside the potato because it's acidic. It's going to take this electron here and it's going to make hydrogen gas. That's what's happening. So it's not always the same reaction, but at the end, one is positive, the other one is negative. And this is called reduction, which doesn't make sense. There's no way it's reduction. But you can see the reaction here. So the copper, okay, the copper is giving the electrons. The copper is supposed to be positive. Yeah, copper is positive, and this is negative. So that's the idea. I'm not going to go into details because I don't know much about chemistry, but you see here you have 3 potatoes, okay, and this is called in series because plus is connected to minus, minus is connected to plus, and here you can measure the voltage. So each potato is about 1 volt. You can do the experiment if you want. Interestingly, if you bring them together, you're going to increase the voltage. That's if you want extra credit, for example, and then you can turn on a LED. So this is fake. You cannot turn on a light bulb like this, but you can turn on an LED. But LED, you need 2 potatoes because 1 potato is 1 volt. LED, you need 1.7 volt because it's a semiconductor. So you need 2 potatoes at least. LED doesn't need a lot of current, but it needs 1.7 volt. So anyway, here you have some values for potential difference or voltages. So you see battery here and outlet. Outlet here is 120 volt, just to give you an example. So from the outlet, each coulomb has an energy of 120 joule relative to ground, because the outlet, there is no negative, right? It's the ground. It's coming back through the ground. EKG, something like this. It's all voltages. Okay, so the thing to understand is that voltage is a property of 2 points. So if you want to be electrocuted, not that you want to be electrocuted, but you see this is 100,000 volts or more, the high tension line. If you are connected to ground, and this is a conductor, of course you're going to be electrocuted, okay, because you make a path for electricity to flow. But it's not so much the voltage that kills, is the current. When current goes through, because we are an electrical system, it goes for your heart will contract, and that's it, right? But this is a very famous picture. I don't know what it's called, a glider. So he ended up on those very high tension lines, and he was fine because there is no 2 points, it's just 1 point. You see, so this is 100,000 volt. He is at 100,000 volt, but because he's not touching the ground, he will be okay. The birds are okay because you see here there is no insulation. Okay, they don't want to put rubber because it will cost too much money. So it's not insulated. It's bare. Okay, it's bare. So it's he's gonna be fine. I don't know. Looks a little bit scary, but a voltage is a property of 2 points. It's only if you are connected to the ground that you're going to be electrocuted. So in that experiment here, she's standing on something that is insulating her. Okay, so this is a Van Graaff generator, no electric field inside. So if I try to trick you, there is no electric field inside, never ever, no charge inside, no electric field inside. Electric field inside the conductor equals to 0. Not if it's not conducting. Not conducting, yes, you can have an electric field. If it's conducting, no electric field inside, remember? Now, she's touching it. So all those electrons or charges will flow here, cannot go inside because she's conducting, will go outside. So that's why the hair rise. but the voltage is the same. So this is 100,000 volt. Her body will be at 100,000, and yet she doesn't die. Even if she was connected, she will not die because there is not enough charges moving. But anyway, she doesn't get shocked because she insulated. So this is called an equipotential. Her body is at the same potential as the Van Graaff generator. If someone touches her, there is a path to the ground, so electrons will move to the ground or from the ground to her, and that's when she will get shocked. Okay, so it's not the voltage that is so dangerous, it's the charges moving. And the Van Graaff generator, you don't have enough charges to harm. Okay, something to remember, a positive charge wants to go from low potential to high potential. No, correct me. A positive charge wants to go from, it's like voltage is like altitude, right? So a positive charge wants to go from high potential to low potential, right? Because it wants to go to a lower potential level of potential. So positive charge, remember, voltage is like altitude. Positive charge is like a mass. So it wants to go from high potential to low potential. That's how it will lower its potential energy. A negative charge will do the opposite. Negative charge wants to go from low potential to high potential. Because imagine, high potential means positive. That means negative. So positive and positive repel. So positive charge wants to go downstream, and negative charge wants to go upstream because it has a critical mind. Whatever it's you say, it wants to do the opposite. Okay? So if you have a negative charge here at B, where will it go? Left, right? To A. If it's positive, it wants to go to C. Is that clear? Conceptual question? Okay, so simple application in the air. You have about 100 volt per meter. So between here and there, you have 100 volt, but it's fine because I'm short. It's like a short circuit. So now my two hands are the same potential, and there is not enough charge to do anything to me. But there is this potential here per meter. So that will be the electric field. Okay, so the electric field again is the voltage per meter. Okay, you can think of the electric field as it's like a slope. 100 volt per meter. So you can so if there is thunderstorm, you have 10,000 volt per meter. So 10,000 volt is like a slope per meter. So what's going to be the voltage for 2 kilometers? It's easy, right? It's a proportion. Ouch. 2 million, 20 million, 20 million, right? 1, 2, 3, and 10,000. So 10,000 times 2,000, 20 million volt between here and there. Are you with me? Do you agree? Okay, you just have to use the equation. You see, delta V equals E delta Y. Okay, so this is the electric field is going to be uniform. So you just use this. So this is plus, 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 because in a cloud you have friction. So you have a separation of charge. So if this is plus, and then the ground is like a reservoir. So you have the minus here. So the voltage is like altitude. That will be 20 million. volt, and that's going to be 0. And then you're going to decrease the voltage up until you get to the ground, which is 0. So what does it mean? Again, the voltage, it will be the work that you will have to do to bring 1 coulomb of charge upstream. By definition, potential energy is always the work that you have to do. Is that clear? Right? So if you understand the concept, everything else is math. So of course, you're going to have some calculus. It's just a review. So voltage is the electric potential energy per unit charge. The voltage is actually a property of 2 points. You say the voltage, it's a difference, a potential difference between 2 points. The voltage, you need to have 2 points. If the electric field is not uniform, you need to use a integral. Minus means that if you want to increase the potential energy, you have to do work against the electric field. So it means the electric field is fighting against you because it doesn't want you to increase the potential energy. Anything wants to go back to the lower level of energy. Okay, so we have seen that if you want to do if the electric field is not uniform, okay, between A and B, first it's going to be very hard, and then it's going to get easier because the electric field is decreasing. So the work done will be the integral under the curve, right? We have seen that just before. Okay, so it's a work done. Work done, force times displacement. The force is the electric field. The displacement, you can divide this distance here. It's in small segment. Agree? Right? It's not that hard. So you can think, you can help each other. So you can do it two ways. You can trace a graph, or you can think imagine this is you here, and you have a positive charge in your hand, and you push. So this is strong, this is weaker. So think about it, help each other. You can do the graph, or you can imagine here, okay, you have a positive charge in your hand and you're pushing against. Where is it going to be the hardest? The hardest. Let me know what you think. You can think of that in terms of integral, right? From A to B. So what will be the largest area? See, very good, right? So what's happening? First, you have to push really hard. Then it gets easier. So this one will be, so this one is the opposite, right? First it's no, first it's easy, right? And then it gets very hard. But here it's easier because you see the electric field decreases, so it gets easier. Okay, here it gets harder, and here it's the same. So if you look just at the beginning, here and there it's going to be the same, except here it's getting harder, here it gets easier, and here it's the same. But you can do that with an integral. Right? So the work that you will be doing, moving that positive charge, is going to be the voltage between A and B. So VA minus VB will be equals to this integral E delta S. Okay, so just applying equation. That comes from an algebra-based textbook. You just apply the equation that delta V equals E delta S. Oops. So don't stare. Do it. Right. You can think of that as delta V equals E delta S. Now, if the electric field is uniform, then I can write that down, or I can say that the electric field is delta V over delta S. So it's like a capacitor here. So this is positive here. This is negative. And this is 64 volt. It's minus, but so that means this is plus, higher voltage. And you can imagine this is the ground. You go from 64 volt to 0, and you're gonna go down at a constant rate. Okay, so just apply this, right? So, and the distance, that distance here is 0.032 meters. 1, 2, 3, 1, 2, so 3.2 centimeters. Right? So the electric field is a slope. So delta V over delta S, which is 64 over 0.032. So it's going to be 2000 volt per meters. Is that clear? So it means the voltage is going to decrease at a rate of 2000 per meter. So you can say, or 20 volt per centimeter. So every centimeter, 1, 2, so every centimeter is going to decrease by 20 volt. One. So that's going to be about. So 64 minus 20. 44, about 40 volt, right? And then minus 20, 24 volt, and then minus 20 is going to be 0. So the voltage decreases by 20 volt per centimeter. That's the meaning. Go from 64, minus 20, minus 20, minus 20, if you forget about the 2 here. So you have to think of voltage like altitude, and you have to think of an electric field as the slope. It's the slope. Okay, so to answer the question, so what did you find? So the electric field is 2000 equals delta V over delta S. So delta V, which is 3 over delta S. Okay, is that clear? Okay, so, and you find delta S equals 0.0015 meters. Okay, so what's the meaning? The meaning is that the electric field is a slope. It's going to be important for next test, not tomorrow or after tomorrow, but the voltage okay, as a distance S, I should say delta S, the voltage is decreasing at a constant rate. It goes from 60 volt to 0. The slope is 20 volt per centimeter. The slope is the electric field. Yes, now you have to remember that the electric field is the slope of the voltage. That's a different way to look at it. I didn't lose anyone. Okay, that's why we need math, right? Because when you look at this equation, it has a meaning. That meaning is slope. When you have a physical quantity and you divide by the distance, that's a slope, a steepness. How steep? If you divide by the time, that will be a rate. How fast? If you divide by the distance, that will be how steep. You decrease, you go down. How steep? It's a slope. The steepness. It's a function. So we're going to say that the electric field is like a restoring force, right? It's a restoring force for 1 coulomb. It's derives. Okay, that's what we're going to say. Derives from voltage. Or that the electric force derives from a potential. So each time you have a restoring force, it's going to derive from the potential mathematically. A restoring force derives from a potential. Are you with me? So if you remember Hooke's law, like if you are doing work, here I'm storing energy in the resistance band, boom. So the potential energy stored is 1/2 k x squared. Remember that from physics 1? If I take the derivative, what do I get? If you take the derivative relative to x, if you take the derivative relative to x, huh? Okay, kx. And what is kx? Oh, that's the restoring force. So each time you have potential energy, you derive and you get the restoring force. Restoring force wants to lower the potential energy. So lots of application in chemistry. Okay, so yeah. Okay, so it's just a simple application here. So you see, this is a capacitor. So 2 plates, one positively charged, one negatively charged. Right here, charge my capacitor. I'm going to disconnect it and I can show the electric field. You see, the electric field wants to bring them back together. So it could have, you could have a breakdown, but in that case, no. And energy is being stored inside your electric field. So all the work done by the battery has been transferred to the electric field. So inside here, you can even define a density of energy density. So anyway, the energy is being stored inside here, inside the electric field. So this is high potential, this is low potential. So if I take a voltmeter, see, this is my ground, this is higher potential, and it's going to be whatever I started with, okay, about 1.3 volt. So the voltage here is higher by 1.3 volt relative to the ground, which means if you take 1 coulomb of charge and bring it there, it will take 1.3 joule. Okay, if you have an electron leaving from minus to plus, it will deliver 1.3 eV. Okay, so anyway, so your voltage here goes from 10 to 0, and you see here Can you find the electric field? So find the slope. Find the slope. You go from 100 volt to 0 volt over a distance of 1 millimeter. What's going to be the slope? So delta V equals 100 volt. Delta S is 1 millimeter. Don't stare, do it. It's a slope. It's a slope. So it's going to be yeah, 100,000 volt per meter. Newton per coulomb. So if you have a proton here, it wants to go down the potential. An electron here wants to go up the potential. Okay, so this is like 25 volt. You are losing 25 volt divided by 1, 2, 3, 4. So it's 1 millimeter divided by 4, which is 0.25. Is that right? 25. And you get right, 1, 2, 3, 4. Right. Okay. So that comes from, maybe it comes from your book. I think it comes from your book. Okay, do it. Okay, this one is easy. So help each other. Ay, ay, ay. So you have a proton. So you have an electric field which is uniform. So the electric field is 1.5 times 10 to the 7 volt per meter or Newton per coulomb. And you go from A to B and you have a positive charge. Oh, it's a nice review, by the way. Okay, so there will be a force. So he wants to go downstream. Right? So a proton wants to go with the field lines, an electron wants to go against. So it's going to accelerate. So it has potential energy, turns into kinetic energy. Right? You get that? Is that 2.4 times 10 to the negative 4, no? Right? No? No, it's not good? No good. So what is that? Or 10 to negative 12? Oh, okay, okay. Yes, because it's minus 19. Okay. Newton. Okay. And B, the work done on it by the field. So it's the field that wants to bring it back to a lower level of energy. Okay, so a work is the force done by the field on the proton times, so it will be the force times the displacement. And it has to be positive because you see it increases its kinetic energy. So when work is positive, that means that the change in kinetic energy is positive. It tries to make it go faster. Okay, remember from physics 1, work equals change in kinetic energy. So it will be 2.4 times 10 to negative 12 times 0.5. So it's going to be 1.2 times 10 to negative 12 joules. Unit is joule. Okay? Potential. So the potential is E. Okay? So the potential will be the work done per 1 coulomb. 1 coulomb. So delta V will be the electric field, which is 1.5 times 10 to the 7 times 0.5. Is that right? So delta V will be 0.75 volt. And remember, I have to be careful with the notation. So notation goes that VA minus VB. Okay, so that will be the voltage VAB. So property of 2 points. It's going to be positive because high upstream, so it's like upstream. When you go upstream, it's always higher voltage than here. But if they ask you VB minus VA, that will be the opposite. So upstream, it's higher voltage than downstream. Okay? So you see here the voltage decreases at a constant rate, right? So these are called equipotential. This is an equipotential. This is an equipotential. Same potential all over here. So think of voltage like altitude. So if I go back to the Van Graaff generator, and here they have the same potential. So the girl and the Van Graaff, it's an equipotential. And the guy, I don't know if it's a guy, probably to end up like this. So it's going to be an equipotential also. So you can define equipotential. You have to understand, you have to think of equipotential as contour lines. Like, see, like if you have a map here, you can go, if you go hiking, you cannot have like a 3D map, right? You have a 2D map. So to show the steepness, you have to make contour lines. So it works the same with the equipotential. Now, the slope, you can find the steepness here. The steepness, if it's very steep, those contour lines will be very close to each other. Okay, and you know it's going to be hard. And gravity will show you how to go down slope the fastest. So it works exactly with equipotential. The electric field will be the slope. It's like gravity, showing you which way to go. So you go the fastest from higher potential to a lower potential. So let me show you. If you have a point charge, okay, so you have the electric field here, and I can find the voltage here, values. See, I can make contour lines. As I move away, the potential is going to decrease. You might think, okay, how come it's just one value? And I told you it's a property of 2 points. But the voltage that you're going to have here is relative to infinity. So it means that if you take 1 coulomb of charge, and you're going to bring it up the potential, okay, 1 coulomb of charge, and you have to push. It's very hard. You go up the mountain, up the hill. To place it here, it's going to take 5 joule of work. So from infinity to here, 5 joule of work. So these are equipotential. Okay, and you see, what you see here is the electric field. The electric field is always perpendicular to the equipotential. So you have to think of voltage like altitude, like contour lines. The electric field is showing you the steepest slope. And if you take calculus, what do we call that in calculus 4 or I don't know 3? The steepest slope is called the gradient. Okay, it's the gradient. So you see the electric field will be the gradient of the potential. So it says 25 volt. So it means it's going to take you 25 joule of energy to go up the potential, and you have it here. And it's not very happy here. It wants to go down slope. Is that clear? Now, how much work you have to do? So let me ask you, I'm going to try to trick you. If you go along that equipotential, do you have to do work? Do you have to work against the electric field? No. No, because the displacement is perpendicular to the force. It doesn't take any energy. So likewise, if you are on a mountain, you're hiking, and you stay on the same contour line, that you don't have to fight against gravity. So if you move a charge, so you are here, you have a charge in your pocket, you have a positive charge in your pocket, it's no effort here. You don't have to fight against the electric field. If you go this way, you have to do work against the electric field. If you go that way, it will be the opposite. The electric field wants to do work against you. Is that clear? So this is a point charge. And if you look at the potential, what it looks like in 3D, looks like if you just have a point charge, okay, forget about the other one. So this is a dipole, but if you have a positive charge, the potential looks like this. Okay, it's like a mountain. So at the top, it's going to be infinity, and as you move away, the potential is going to be 0. If you have a negative charge, it's going to look like that. So if you want to do, if you want to take a positive charge, you have to fight against the electric field. So these are called equipotential. And we can show, so I recommend that you take your textbook and they will do the calculus for you. But you can show that if you have a point charge and if you want to bring it at the distance r, okay, so what's going to be the potential here at a distance r? You need to find the work it takes to take 1 coulomb of charge from very far away, push it to there. So that will be the potential relative to infinity. How much work is done to bring 1 coulomb of charge at that distance r? And if you do the math, you get to this equation here. So for a point charge, okay, the voltage, these contour lines will be inversely proportional to the distance. And it makes sense because the electric field, remember for the test, the electric field follows a inverse square law. So 1 over r square. So if you divide by 2, the electric field will be multiplied by 4. Okay, if you multiply the distance by 3, okay, between the 1 coulomb and your charge, the source, multiplied by 3 the distance, the electric field will be divided by 9. There is one conceptual question. So if you take the derivative of 1 over r square, you have 1 over r. No, not derivative, integral. If you take the integral of 1 over r square, you're going to get 1 over r. Is that clear? And it's done here in your book that you need to open. Okay, they show you the math, beautiful math here. You see, you have to take the integral of 1 over r square, blah, blah, blah. And that's what you're going to get. You go from here to there and they do the computation. And then they decide. So the voltage is per unit charge. So Q equals 1. And at infinity, we decide that the voltage equals to 0, so the potential energy equals to 0. So they do the computation for you. Any question? So again, it's like contour lines, okay? And so these are the potential. The electric field will be the slope. Okay, so if you have a uniform electric field, you see the slope is constant. So this is uniform electric field, the slope is constant. In this case, okay, if you have a point charge, is the slope constant or no? Do you want to climb that? No, the slope is not constant, right? It's going to be very large at the beginning, and as you move away, it gets gentle. Okay, so it's not uniform. You can see here the lines are packed together at the beginning, and then they are farther away. Okay, so as you go against the electric field, first it's going to be easy, and then it's so hard. It's like climbing. You go hiking, you say, oh, okay, that's not so bad. And then you get to the summit, and it gets harder and harder and harder, and boy, it gets so hard. Okay, so we'll do that next time. But you have to so you have to open your book. So now if I take a dipole, okay, I can take a dipole. What do you think the potential is going to be here? Positive or negative? It's going to be negative, okay? It's a negative potential. So this is a throw and this is a crest. And in between them, it's going to be flat. No potential. So it works like altitude. Yeah, isn't that cool? Now, from very far away, remember the electric field goes down as 1 over the distance q. So that's why you have this picture here. If you have a dipole up and then it goes down. So if you have a positive charge here, it wants to go down, 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 down. And this is far away. This is negative potential, positive potential. Yeah, same thing here. So this is so that will be Van Graaff generator, for example, negatively charged, positively charged, same potential inside. So potential doesn't change. And you're gonna have something like this. Okay, there is so much you can take.